Hey, okay, so real quick, I'm going to go over electron configuration. So remember that through light, Bohr determined that energy levels exist within the electron cloud. So before Bohr, they knew electrons were out in a cloud, and they knew that there was a nucleus, but Bohr was the one that figured out that they were actually arranged in energy levels. And then really, scientists like Schrodinger and Rydberg, who were theorists and guys that dealt a lot with probability and math, they figured out that sublevels actually exist within each energy level. So here's the difference, really. Bohr thought that they were kind of orbiting the nucleus, almost like planets in orbit around the sun. But Schrodinger and these other guys figured out that you can't really pinpoint the location. It's not as easy as that. There are areas where they're more likely to be found, but there's no way to pinpoint the exact location of an electron. And it's not moving in a predictable circular pattern. Instead, they're just going to be found within areas of probability. So those are called sublevels, and you have the S sublevel, which has one orbital. Now each orbital contains 2 electrons. So an S sublevel can hold 2 electrons. The P sublevel actually has 3 orbitals. And so 3 times 2 gives us 6 electrons. So that actually explains why there's 8 electrons in the second energy level. If it has an S sublevel and a P sublevel, 2 and 6 together make 8. So the pattern that Bohr found with the numbers of electrons per energy level actually started to make more sense after this. And then the D sublevel has 5 orbitals, and that's going to be 10 electrons total. And then the F sublevels have 14 electrons because they have 1, 2, 3, 4, 5, 6, 7 orbitals. So each orbital in a sublevel holds 2 electrons. Don't know why I forgot the S, but it holds 2 electrons. And we can use an electron configuration to describe the location of every electron in the electron cloud. It's kind of like an address. You know how there's addresses for every house in the neighborhood? You can find a house by looking at the number and the street. Same way with the electron cloud, okay, with the electron configuration. So there are 3 rules we use whenever we're doing this. First being the Aufbau principle. The lowest available sublevel must be completely filled before electrons may occupy the next sublevel. So what that means is, if we're looking at this orbital diagram right here, we always have to start with 1s. Okay, we always have to start filling up here and then work our way up. Hund's rule says that every orbital in a sublevel is occupied by a single electron before any orbital is double occupied. Okay, so we fill up the 1s, it's full, we go to 2s, it's full, we go to 2p. Well, when we get to 2p, we have to spread out the electrons. Remember that they all have a negative charge. They don't really want to be that close to each other. So they'll spread out, and each one will fill an orbital before we go back and put the second electron. So that's Hund's rule right there. And then the Pauli exclusion principle says that no 2 electrons may occupy the same orbital with the same spin. So remember that electrons, again, are negatively charged. If one is spinning in this direction, it's going to push the other electron in the same orbital in the opposite direction because of that force of repulsion. So we always draw it with 1 up arrow and 1 down arrow in the blank, okay? And so once we've figured out how many electrons we've got, we just start filling it up in order. Remember that the number of electrons should normally be equal to the atomic number. Unless it's an ion, we would add or remove electrons for an ion. But for a normal atom, it should be equal to the atomic number. And I should have spread that out first, but I didn't. So let's say that I had this element right here. So I filled up the 1s with 2 electrons. Then I filled up the 2s with 2 electrons. Then I filled up the 2p with 6 electrons. 3s filled up with 2 electrons. 3p filled up with 6 electrons. Then 4s was next, 3d filled up with 10, and then 4p only has 2 electrons in it. So actually, this has to do with the periodic table, right? Hold on for just a second. I'm going to run and grab a periodic table. You'd think I'd always have one laying around, but I really didn't this time. Remember that the periodic table also shows us the order that they fill up. First, we have the 1s, right? Fills up with 2 electrons. And then the 2s fills up with 2. And then 2p fills up with 6. And then 3s. And then 3p. And then 4s. And then this is the 3d sublevel. It actually fills up after the 4s. And then we had 2 electrons on the 4th p sublevel. So that would be germanium. And if I added up all of these little superscripts right here, it should add up to the atomic number of germanium. Okay? Remember that if it's an ion, you add or subtract from that number. So if germanium had a charge of +2, I would take off the last 2 valence electrons from its electron configuration. And if we're writing an abbreviated electron configuration, so for germanium right here, what I would do is I would look for the noble gas before it. That would not be krypton, because krypton's 36, germanium's 32. So the noble gas before it is going to be argon. And I would simply write the symbol for argon in brackets and then work my way from there. So argon is 3p. So after that, I'd have to do 4s2, 3d10, 4p2. So that would be the abbreviated electron configuration for germanium, this very same element. Okay?